All right, let's talk about X-linked traits. So this is different than the normal genotypes and phenotypes we've been talking about. So normal genotypes would look something like this. So let's just use the letter B. An individual could have two dominant alleles, they could have two recessive alleles, or they could be heterozygous and have both a dominant and a recessive. You could also do a Punnett square with this, where maybe mom had big B, little b, and dad had little b. You cross everything in the Punnett square. So this is just kind of regular old Mendelian genetics, genotypes and phenotypes. X-linked is a little different because it's specifically linked on a chromosome. So let's talk, we got to talk a little bit differently about this. So let's make some room here to talk about X-linked. When we're talking about X-linked, we have to kind of go back to what that means. We need to talk about the chromosomes. So in humans, we have 46 total chromosomes. We get 23 from mom and 23 from dad. Okay, and that's going to come together to give us 46 chromosomes. All right, because we have two of each, or I'm sorry, we have a pair of each chromosome. So like chromosome number 1, we get one from mom and one from dad. Those are my little chromosomes. Same for chromosome number 2. We get one from mom and one from dad. Okay, so on and so on. Our 23rd chromosome, which is our last chromosome pair, so number 23, that's our sex chromosomes. Okay, so for females have two X chromosomes. Males have an X and a Y chromosome. Okay, so that's our last chromosome pair. And this is what decides the sex. That's just what decides if we're male or female, or that chromosome pair number 23, which is our our sex chromosomes. So again, females have XX, males have XY. Now, when we're talking about an X-linked trait, we're specifically talking about genes that are linked to the X. Okay, notice I did not point to the Y, because when we're talking about X-linked traits or X-linked genes, we're specifically talking about the X chromosomes. So this means that women or females are going to have two alleles for an X-linked gene, but men are only going to have one because they only have one X chromosome. Their other chromosome is Y, and we're talking about X-linked, so they're only going to have one. All right, so keep that in mind while we're talking about this, and it'll make a little more sense as we kind of go through this. So let me make some room again. Let's get this kind of out of the way, and let's do some examples here. All right, so let's talk about a disease called hemophilia. And this was a disease, it's a blood disorder that most famously ravaged royal families back in the late 1800s and early 1900s, and started with Queen Victoria in England. So you should check that out if you did not see the video from class. But basically, it's an X-linked trait. So that means it's found on the X chromosome, and it's also recessive. So let's just use the letter H for our genes or our genotypes. So that means the dominant allele, which is going to be designated by uppercase H. As always, it's uppercase if it's dominant. That's going to be the normal allele. And then the recessive allele is going to be hemophilia. Okay, so big H is normal and little h is hemophilia. So we're going to stick with that. Now let's talk about kind of how this would look when we're talking about males and females. So females are going to have three options. Okay, XX, XX. So they can either have big H, and notice I'm just connecting the allele. Sorry, that H looks kind of bad. I'm connecting the allele to the X chromosome. So I write it just up to the top right of the X chromosome because it's going to be linked to the X. So wherever this X goes when we're doing Punnett squares, that allele is connected to it. Okay, so you can have two dominant H's. You can also have two recessive H's, or you can have one dominant and one recessive. Okay, now let's go to the top female here that has the two dominants. Well, she has two normal alleles. That means her phenotype is going to be normal. She's not going to have hemophilia. Now this female in the middle here, she has two of the recessives, and the recessive trait is hemophilia. So this is the way that women can have hemophilia, is if they have both recessive alleles. That means she got one from mom and one from dad. Now this last one here with the heterozygous, of course we know dominant's always going to win, and dominant is normal, so this female is also going to be normal. So the only way that a woman can have hemophilia is if she has two of the recessive alleles. Okay? Now let's talk about men. Okay. So let's move this up here, keep our females in our eye line still. So here's males. They only have two options, because they only have one X chromosome. So they're either going to have a big H or they're going to have a little h. That's it. If they have the big H, they're normal. And if they have the little h, they're going to have hemophilia. So what's kind of a disadvantage here for males is that they have a higher chance of having the disease because they only need one bad allele or one of the hemophilia alleles to have the disease. Women kind of have this extra chance here where if they have one of the bad alleles, they might have this kind of extra buffer because they can have this dominant normal allele that can hide that. All right, so they kind of have this backup plan that men do not have. So males are more likely to, or actually they have a higher chance of getting this disease than females do. And I do want to note here, just because I just pointed to it, that this is specifically called a carrier. So women that have one normal allele and one of the diseased alleles, they're known as a carrier because even though they don't have the disease, they do carry the allele for the disease that they can pass down to their children. So if you ever see the word carrier, it's talking about a heterozygous genotype because they're going to have the normal dominant trait, but they do carry that hidden recessive trait in their genes that they can pass down to their kids. So just some terminology you need to be familiar with. All right, so let's move into doing some Punnett squares with this. So let me kind of get rid of some stuff here. Get this out of the way. And I'm going to kind of keep this up so you can still see it. So you can refer back to the genotypes. And let's go ahead and draw a couple Punnett squares. So let's start with mom and dad, just using the X's and Y's. So you always want to start out like this because of course you have to have a female on one side and a male on the other. There's no other possible way to have a child. So you have to have XX on one side and XY on the other. Now we can fill in our genotypes. So let's say I told you that mom is a carrier. Well, if mom is a carrier, that means she's going to have this genotype. She's going to have one normal dominant allele and one hemophilia recessive allele because she's carrying the disease even though she doesn't have it. Dad, on the other hand, is going to have hemophilia. So if I say he has hemophilia, the only thing he can have is a little h. All right? Notice I didn't write anything on the Y again because this is an X-linked trait. And now all you do is cross everything in. So you're going to bring these two X's in. One has a big H, the one from mom, and the one from dad has a little h. You bring these X's together. Mom gives a little h. Dad gives a little h. Bring in the X and Y. Mom gave a big H. Put another X and Y. and this time mom gave little h. Okay, so there is the probability for your kids. So if you look here, you have, if they have a daughter, which would be these two right here, there's a 50-50 shot that their daughter can have hemophilia. Because this daughter right here can have the disease, but not the other daughter. If they have a son, which would be these two guys, again, they're going to have a 50-50 shot because this son would have the disease. So both the males and female children that they had would have a 50-50 shot. All right, so let's do another one. I'm going to delete this one and start over. So let's say, let's do mom, dad again. And let's say mom is a carrier again. Let's do mom as a carrier. Okay. And let's say dad is normal. Okay. Let's cross in again. Notice I always write the big H's first. It's just kind of a rule of thumb and a habit you should get into. And notice again I'm not writing anything on the Y's because it's X-linked. Okay, now if we look at this one, if we look at their daughters, which are just both of the XX's, there's no way that their daughter can have the disease because both daughters are going to show the normal phenotype, even though one daughter could be a carrier as shown here. Okay, but if they have a son, there's a 50-50 shot because this square right here indicates a male that has the disease. So this shows you why males or are more likely to get the disease, or they have a higher chance than females do. Because females still kind of have this backup plan that they could get a dominant that will overpower the bad allele. So as long as you kind of understand this, this is really what you need to know about X-linked. You need to be able to understand how the genotypes are written, how the phenotypes are figured out, and you need to understand how to do a Punnett square with these. So hopefully you've learned something from this and you can do this by yourself now.